We are now going to talk about another model of growth, the Solo model. And the Solo model is a dynamic model of growth, unlike the steady state, single solution classical model that we looked at previously. And this Solo model allows investment, and because it allows investment, K can increase. It doesn't remain at a fixed value. It is an extension of the previous classical model, but it adds this dynamic dimension to it. And that's a picture of Robert Solow there. He is 91 in the year 2016, and he is still active as an economist. So let's set up the model. So the production function is exactly the same as before, except we're adding a time subscript. So for example, Ct plus It equals Yt is saying that in the period number T, consumption plus investment equals total output. So what we're really adding here is capital accumulation. Now, to make the story plausible, we have to have depreciation as well as accumulation, because if there's no depreciation of capital, capital could grow forever to an infinite level. In the case of consumption goods, there's no problem about them accumulating forever because you have to consume a consumption good in the period that it is produced. There is no storage of consumption goods. Here is the capital accumulation equation, and it says that the change in capital stock is equal to the amount of saving that you do minus the amount of depreciation that happens. Now this savings is also equal to the amount invested. The two are exactly equal to each other in this model. Now you see the bar over the S. That means that the savings rate is an exogenous parameter given to us. It has a fixed value, so at this point people don't get to choose how much saving to do. Likewise, the depreciation rate is a parameter. It's exogenous. You don't get to influence that depreciation rate. By the way, a small technical point. For this model, when you start out in period 0, you have to give an endowment of capital to the economy, because in period 0 you don't have capital that you've created in an earlier period. In period 0, if you don't give the country some capital, they won't be able to produce anything, and they will remain stuck at 0 production, 0 consumption forever. As for labor, we're just going to assume that it's constant, and if we wanted to talk about population growth, we could do that. In this kind of model, population and labor force are exactly the same amount, the same thing. Everybody works. There's no retirement. There are no children. So, going straight to the summary of the model, there are 5 unknowns, and there are 5 equations, and there are 5 fixed parameters that are just given to you. Notice the k-bar 0 there at the bottom. It has to be a positive number. So, like the previous model, these are the equations that you solve, and you can solve them because there are 5 equations and 5 unknowns. We are not actually going to work out the equations. We're just going to consider the sort of solution you have by looking at a diagram. This diagram shows a horizontal axis that measures the amount of capital stock at a particular time period, and the vertical axis simultaneously measures investment and depreciation, and it also measures output, although the output line is not drawn in this diagram. So what you see is, since depreciation is a constant proportion of the capital stock, it's a straight line. On the other hand, we're going to assume that investment is a proportion of total output, and we know that total output has a diminishing marginal product of capital dimension to it. So as the capital stock goes up, output goes up, but it does not go up in a linear way. It goes up in a declining slope way, and investments, which are a proportion of output, will have the same kind of shape. I'm actually going to repeat the same diagram again in this slide to make it easier to talk about. Now, as you see, you have a K star right there in the middle. That's the equilibrium long run value for K. Now, how do we get to K? Well, we get to K in the following way. Let's imagine we're starting with a K that is smaller than K star, like the K0. If you look at K0, total investment is greater than depreciation. What that means is that after a couple of periods with investment exceeding depreciation, the capital stock will keep getting bigger. That's why if you start out at a point like K0, the arrows are pointing to the right. Now let's look to the right of K star, the right part of the diagram. If you're at that relatively high level of K, you see that depreciation exceeds the value of investment. If depreciation is greater than investment, there's a net negative effect on the capital stock. The capital stock is going to decline, and that's why the arrows are pointing to the left. The only place where you have a balance between the force of depreciation and the value of investment is at that K star. So the point of this diagram is, if you start out at a place like K0, you are inevitably going to move to the right along the capital axis. If you start out at a point far to the right, you are inevitably going to see a decrease in your capital stock, and the equilibrium, the stopping point, is where investment line and depreciation line intersect. And so once you reach that point, the K star, you will stay there forever, unless something happens to shock the model and change some values. Now, this is an equilibrium. It's a different sort of equilibrium from the previous model. In the previous model, we just wrote down a bunch of equations and we instantaneously solve them, and magically we have the equilibrium solution. In this kind of model, our notion of an equilibrium is a place you converge to. It's a place where you end up. It's a place where you don't necessarily start out, but you get there eventually. That's the notion of what equilibrium means in a dynamic model like this one, where there's change over time. Dynamic model means change over time. Okay, this is the same diagram as before, except that I have drawn in the output curve. Now the output curve has the same downward sloping sort of tendency as the investment curve. The investment curve and the output curve are related. Investment is a fixed proportion of Y. So whatever the shape of output is, in the investment curve will have the similar shape. Depreciation is the same. The depreciation line hasn't changed at all. So what you see then is, as we do that sort of movement toward equilibrium K star, the output level is going to be changing to match it. And if you reach K star, you stop there forever, then you know what consumption per capita in this economy will be, because it's that vertical distance, the distance between total output and the amount of output that is being used up in investment. Now this version of the diagram is kind of important. It's important because it's showing explicitly what consumption is. And consumption is the thing that we really care about in this model. At the end of the day, the whole reason for having economic growth is to maximize consumption per capita. So being able to measure that distance of consumption is sort of like a measure of how successful the economy is. So we can solve the equations to arrive at actual numerical values for equilibrium y and equilibrium everything else, actually, and the textbook works through it all. I'm just going to jump right to the final equation, and the final equation says that output per capita is equal to that function on those values on the right. Now you can forget a bar because that's just a number that's given to you. The thing that has some intuition is the S bar divided by the D bar. If you think about it, what's it saying? It's saying that everything else equal, if you have a higher S bar value, total output will be higher. If you have a higher D bar value, everything else equal, you will have a lower equilibrium output value. And that sort of makes sense. The higher is your saving, the higher you expect the equilibrium capital stock to be. The greater is depreciation, that's the sort of negative thing. The higher is depreciation, the lower your equilibrium output will be. Now, technically, S bar and D bar have limits on their values. They have to be between 0 and 100%. However, obviously you can't have a 0 value for depreciation because that would give you an infinite growth in capital and the model would just become meaningless. So in practice, depreciation has to have some positive value for the model to make sense, and also savings has to have some positive value. Now at this point I want to make really explicit that you should be skipping some pages in the text chapter, and that's also in my notes. Now, there is something that isn't really very explicit in the text, and it's very strange, and the thing that should be explicit is that there is such a thing as a K star, which is the preferred value for K star, the optimal value for K star. It isn't the case that we don't care what the equilibrium K star is. If we get to choose what K star will be, we can decide to choose the K star value that maximizes that consumption that we saw in the previous graph. We want K star to not be too small. We don't want K star to be too big. We want K star to be just right to make that consumption value as high as possible. Now, this sounds a little odd because the natural thinking is that isn't the best capital stock the biggest capital stock in equilibrium? Don't we want K star to be as high as it can possibly be? Well, actually the answer is no. And the reason is this: if you aim for a really, really big capital stock, you will be using all of your output to offset depreciation. It would be like owning a house that is so big that in order to keep it functioning, you're using all of your income. You don't have enough left over for food. So the optimal K-star is not the maximum possible K-star, it's the K-star where that consumption distance is at its maximum. Consumption is ultimately what we care about, not having a big capital stock. We want K to be not too low, not too high, but just right. So how do we choose K-star? How do we influence it? Well, the only way in this model you can give people a way to choose their K-star is to allow them to choose S. So instead of having S be a fixed percent, you let the society choose what S will be. It's like you take the bar off the S and now it's a choice variable. And the idea is that governments can influence that choice of savings rate by tax policy and other kinds of policy. And the Solo model's message is that if you want to have maximum consumption, you have to aim for maximum level of capital stock, and to get the optimal level of capital stock, you need to have a government with encouraging the right amount of savings. Not too high savings, not too low savings. And that's the message of Solo model. Actually, growth is all about getting to the right level of savings, and through that, the right level of K. So the Solo explanation for why countries are poor is that they don't have enough capital, or maybe, less likely but possible, they've overinvested in capital and they're spending all of their output maintaining the capital. So to Solo, if your country's poor, it's because your investment is at the wrong rate, at the wrong level. It's an investment problem. Capital creation is not right. Now, to finish off, we've just said that the Solo model's explanation for wealth or poverty in nations is all about having the right level of capital. Now, unfortunately, and the textbook doesn't really make this clear enough, that the Solo explanation is not plausible in the light of modern economic growth. If the Solo model were true, you'd expect most countries eventually to converge on the optimal level of capital stock and the optimal level of K. And then in the long run, countries would all converge to about the same per capita income. If you look at the data for rich countries, that's not the way it happens. Solo's motivation and thinking is that capital has diminishing returns. A rich country that has a lot of capital and accumulates more capital is going to get less and less benefit from it, less and less output. So that sort of sets a upper bound on how rich you can become. And eventually everyone will hit the upper bound, probably. But if you remember that graph we did really early about the history of modern economic growth in the last 200 years for developed countries actually shows an exponential curve. If you look at the history of economic growth in the last 200 years for the moderate to the rich countries, growth actually accelerated the richer they became. That's totally contradictory to having diminishing returns to capital. So even though the Solo model originally seemed very plausible, in later years economists have decided that it is fundamentally lacking. It just doesn't conform to the way growth has worked out. So economic growth is really puzzling. we don't see the sort of capital-based explanation for growth really working. The next chapter, we will be looking at an alternative way of thinking about economic growth that addresses this diminishing returns problem. So see you next chapter.